Okay. So now this star and star part, they can combine to give you another olefin. So here what we end up having is, we will be having this group having a double bond here. So this is one type of olefin, and CH2 double bond CH2, because these are nothing but the CH2s. So these two CH2s will form a double bond, making it a olefin. So this is your star, this is your star, and these are your dots over here, just to have a better representation. So how the mechanism looks like in this particular case, let's see. So here we have a substrate, and we have a metal carbon. We are not making the full carbon, but it's a metal carbon we are making. Now it actually undergoes a 2+2 addition with this side. On any side you can take, and it would form something like this way. So other end is open. Now again it will undergo retro 2+2. So what it really forms, that it would form a bond over here, and this breaks. So it releases the olefin CH2 one molecule anyway, and it would form M double bond. So it has lost the CH2 double bond CH2, right? Now at this point, again, it would undergo this, and this part would close, and you will end up getting M. So they are closing the path. This is interacting, suppose this one, and this will go here, and this will interact here, and it will give you this part. I'll just draw here this side. After this, when we have this kind of system, so what it would do, that it would make a double bond here, and this bond will break to give you this olefin, and again regenerating the catalyst. And already we have released another olefin, which is CH2 double bond CH2, which is ethene. So this is the way that ring closing metathesis reaction works. And in a similar fashion, we can have a polymerization of these systems. Moving ahead, we have another reaction, which is your Krebs system. Now we have, say for example, this substrate. This is your one olefin. This is like intra-metathesis, right? So now we can see that these are the centers which needs to be connected. Or you can say that this is like star, which has to go out, and these are the centers which are dots, which needs to be connected. So here we are using, firstly, a molybdenum-based straw catalyst with 5% of it. And what we will end up having, we will be having 5-member ring. And now you can see that this dot and this dot is going to play a role, forming a double bond. This was having methyl, and that is also having methyl. Here it was phenyl. Now the left out part is, this one was CH2. So CH2 star, it is going to make a double bond with the carbon having methyl group, right? So this is your another olefin that has been generated. This is the main product. Now that has been found out comparative to Grubbs catalyst, the straw catalyst has less functional group tolerance. So that's why the Grubbs catalyst has been widely used. For example, the Grubbs catalyst, which came in 1993, if you take this example, an example of intra metal metathesis. So here, if X equals to acid, alcohol, CHO, you will end up getting a percentage yield of 87, 88, 82 of the product, which is your cyclic group, because this and this has to form a double bond, and this X remains as such. It will not go any reduction at all. It will be having a high functional group tolerance, which is not present in case of the stock. All right. Moving ahead, now we have another part of it is ring closing metathesis of lines. Basically, this one, SiET3 methyl double bond. So here if you'll see, there is one part of olefin. This is alkyne, and this is again ene, olefin. So when you're using ruthenium catalyst, which is your Grubbs catalyst, what really happens is we end up getting a product which is a 6-member ring followed by a 5-member ring having olefin, and the groups remain as such. So this is the way. Firstly, alkyne reactivity is very high, so you can first react with one olefin and alkyne, and then that alkyne will react with the another one and giving you two olefin over there. Now we have lecture 4, which was about alkyne metathesis. Basically, we have this is a number 7 chain, like it is having CH2, CH2 like 7 times, and it is having an alkyne over here coordinated to methyl. Now in Strock, using a Strock catalyst, which is nothing but the tungsten one, and alkyne and tertiary butyl, and it ends up giving us, this is 5, this is 5, and so this is your product. So this is how we do the alkyne metathesis, and the mechanism that happens here is if we have a catalyst with R and there is another alkyne R dash, so it will undergo 2 plus 2 and forms, this is tungsten R, R dash, this is R. This can actually rearrange because here from X-ray analysis, it has been found that all the bond lengths are equal. So they can actually do the resonance structures, and now it will form R dash and R over here. So if you'll see, now this is going to play So this will form a new Grubbs catalyst, which is WR dash, and new alkyne with this group. Earlier it was R dash R dash, now it is R and R dash. So this is where the alkyne metathesis happens. Now we have another interesting thing, which is the limitations of the Wittig reaction and how the Strock carbene overcomes that one. So we know that what is a Strock carbene versus Wittig reaction, Wittig catalyst. So we know that we have a Strock carbene which is neopentyl tantalum tertiary butyl, and this can be rewritten as this way, where it can have a minus charge and this is having a plus charge and minus area tertiary butyl, similar to Wittig reaction, where we have PPH3 PH3 phosphine double bond R, and it turns into PH3 phosphorus P and minus R group. And when this PH3 plus and this minus R group reacts with a ketone or an aldehyde, so this basically forms PH3PH. This is having R1 and this is having R2. This is H and this is O minus. So when it works, it would release the PPH3 phosphine oxide will release, and therefore it would form a R1, W1, R2, which is your olefin. So it is a basically reaction of carbonyl groups with this organophosphorus compound, and then it would lead to formation of an olefin. So, but this has certain limitations, whereas it fails in case of the esters, whereas Strock carbene can be used in that one. So if we have a Strock carbene here, and now we are treating it with ketones, 2 plus 2 tantalum. So this is your tertiary butyl group, methyl and methyl, neopentyl. Now again retro 2 plus 2. So is going to form in this way. That new bond is tantalum oxide, and your product is tertiary butyl and methyl and methyl. So this is your olefin. So basically, Wittig reaction fails in esters, case of esters, DMF, where these substrates are actually electrophilic in nature. And there we can use a, or we can say they are less nucleophilic in nature. So here, Strock catalyst work. Now we have factor 5, which is your cyclopropionation reaction, but not much has been disclosed in this one. So firstly, we'll talk about the Fischer carbene again. We know that here metal is mostly group 6 the metal, X is OR, NR2, SR2, etc. L is oftenly CO, and metal is having filled D orbitals, which can help in filling the 2p empty orbitals of the carbon. So making it, this is nucleophilic center, and this is electrophilic center in nature. So synthesis we have already seen for this one. Now, can we consider Fischer carbene as a carbonyl equivalent, meaning that we have this, it can be written as XRN plus, right? And therefore, we can also so the lone pair, say for example, if this is oxygen, so lone pair comes, X is OR, lone pair comes and forms like this way, right? Similarly, when we have, so considering that A double bond XR, this is R. If A is your oxygen, so let's make a table of comparison. In this case, if X equals to O, X equals to NR, and we are talking about the rotation barrier of this one. Higher the rotation barrier, meaning higher the electron negativity and therefore more double bond character. So if A is oxygen, meaning we are talking about the carbonyl, the rotation barrier with X equals to O, it's 12. And if it is NR, it is 18. If instead of that we have a Fischer carbene, which is CrCO whole 5 group, this would be 18 and this is greater than equals to 25. Since these values are very, very high, values of rotation barrier is very high for Fischer carbene case. It symbolizes that CrCO whole 5 group has more electronegative character, therefore more double bond character, and hence it can be compared to the carbonyl group. Now there is another property of Fischer carbene, which is interconversion Fischer carbene, which is Cr, ONe, and R, tertiary butyl, and tertiary butanol and methanol. So if I'm having a methoxy group here, and this is a tertiary butanol, it can easily interchange to the tertiary butoxide group here. Or if I'm giving methanol again, it will go back to this one. Similarly, if I have HNR2, so it can easily change the OMe group to NR2 group and R. So this is the beauty of the Fischer carbene that we use. Also, this has application in aldol reactions. So for example, we have this is COO5, a kind of catalyst, and we are firstly using beta-lithium at -70 degrees, and the other part, the substrate that we are having is this one. It has to undergo the aldol reaction. What it would do that the chromium CO5 amino acid, this methyl and this group will connect to CH2, making OH and MEPH. So this is a diastereomer with 94%. So this is another application, and the last application that we are looking into is catalytic cyclopropionation. So we have this group, and we are using the carbene catalyst, Fischer carbene, and it will form a cyclopropane over here. How? In presence of that one, it would release this will have a cyclopropane group. So commonly catalyst that has been used is palladium-2 for diazomethylation, rhodium-2 with copper iodide for N2OR, diazoester can be rewritten as -10. This one. So this is with respect to the week one session, and we have covered all the basic concepts that has been taken into consideration for this one. Just quickly take a recap. Before that, I would like to give certain questions to you, which would be like simple questions based on the understanding of what we have read so far. So the problem session. In case of this, I will give a reaction, and there we need to find out. In case of the substrate, question number one is, in case of the substrate, PH double bond O, this is an acid group, NH double bond O, OMe. So this is your substrate and it undergoes, this is your catalyst, a chiral catalyst, rhodium based, which is your Osborne catalyst, that is also been given, and in presence of hydrogen. And here And here hydrogen. Now, first question that we have in hand is whether it is going to give you S isomer as major product, option B as R isomer as major product, C is racemic mixture. So this we have already explained in details. Why am I giving this question again? That you need to again follow it up and try to solve on your own. First, you understand the mechanism of what is our target. This is the substrate and this is the alkene, which is going to be reduced. So first is to find out the product. First, you find out the product. And the second part of the question is like the product is going to be the S isomer as major, R isomer as major, or there would be a 50-50% of both of them, making a racemic mixture. So since we are using a shock Osborne catalyst, this is basically going to do the olefination, hydrogenation of your olefin, because we are giving a hydrogenation source also. And this is going to be making a single bond. Once we are using a chiral catalyst, the star symbolizes the chiral catalyst, and based on that, we will be having a chiral product. And that chiral product is going to give us this S isomer as a major product, as this follows a Curtin Hammett principle. So I would like you to even further give it a thought and solve it. And maybe I'll change this group as R over here. And you just find out what are the solutions and what is the proper explanation of that one. The second, choose the right combination. Fisher, carving, shock carving, Grubbs catalyst, Tebbe's reagent. So we have on the other side, metal is in low oxidation state. Metal is in high oxidation state. Metal is ruthenium. Metal is titanium. So if you'll see over here, we know that Fischer carbene comes in a category where it has to be in a low oxidation state. So we have A with the combination 1. The shock carbene, on the other hand, it has to be the option B, which is in the higher oxidation state. And it can also follow that metal can be titanium. So both the combinations are correct. Now the Grubbs catalyst that we have, Grubbs catalyst is also part of a shock carbene. So it can be having a metal oxidation state in higher. Generally, it is only having +2, +4 oxidation state. So it can be in a combination of higher oxidation, C, giving a combination of 2, and the metal is generally ruthenium. And Tebbe's reagent is also having D is having a combination of 2 and 4. So it is titanium and metal is in higher oxidation states. These kind of combination can come in the exam also. Followed by that, it's okay. So question number third that we have in hand is for X equals to acid, alcohol, aldehyde group, which catalyst is the most suitable one for carrying out the following conversion. The conversion is so here the conversion is happening. So in presence of the catalyst. So basically this is the metathesis and the options are Krebs catalyst, shock catalyst, Fischer carbene, Osborne catalyst, shock Osborne catalyst. So firstly, answer that we need to see is the given reaction is basically a metathesis reaction. So it can't be performed by D. This one. This is anyway wrong because this is being used for hydrogenation purpose. Only these three used for the metathesis. But since it is having a functional group tolerance, so option A is the right option that we have already discussed. So based on that, the last question that we have is, so now based on this curtain Hammett principle, we are saying that A and B are in equilibrium. So they are in equilibrium. So now you need to find out which one is going to be the major product. So this is actually following your Curtin Hammett principle. And this is your question, like you need to find out on your own. Take the example that we have discussed for the asymmetric hydrogenation, where the S isomer was forming as a major product. Considering that, think about this example. I'll just mention, take the example of asymmetric hydrogenation and find out the possible solution of this one and a proper explanation, like which one is going to be the major product. I'll just tell you that A is your substrate, B is your substrate, which both are in equilibrium. TS1, TS2 is the transition state involved, and we are getting a C and D as product. Where you can see what are the energies that x-axis is giving you the energy, and y-axis is energy, and x-axis is your reaction coordinates that we are not mentioning. Now, based on that and fixing the energies over here, finding out which one is less, which one is more, based on that, you need to find out which one is going to be the major product or which intermediate is going to be characterized and giving you the maximum possible yield of that. So with that, we will just take a brief recap of what we have discussed in today's session, and then we can move ahead with your queries. So basically, this course, as I said, that it is a metal-mediated synthesis. So we will be talking about mini metal catalyst system, which will help in, we will discuss about their synthesis also and various different applications in organometallic catalysis. So what we started with, like asymmetric hydrogenation as the term, where we split it into two terms, asymmetric and hydrogenation specifically. Hydrogenation means like something which is getting hydrogenated, meaning in addition of the hydrogen. If we take an example of alkene, it will go to alkane with the presence of hydrogen and a catalyst. Asymmetric means we are talking about the chirality in that case. Chirality meaning having your groups along that particular center. If you take a carbon as a center, it should be having a coordination number of 4. So in that particular saturated system, so if all the groups attached to that particular center are different, that means they are inducing the chirality. Before moving to the asymmetric hydrogenation, we actually went to see what is olefin hydrogenation means. So why do we need a catalyst? Catalyst is a species which will generally provide an alternative path without getting consumed in the reaction, and this could help you in reducing the activation energy, as you can see from the particular system where if you're not having, this is your non-catalytic pathway where it would be involving more energy compared to the catalyst involvement. Then we moved ahead to see our first catalyst, which is shock Osborne catalyst. This is being known for olefin hydrogenation. This is a rhodium-based catalyst and having a phosphine as a ligand in the environment. So basically, if we have this is the catalyst and it will be having two solvent molecules coordinate to it. We know that something called active catalyst, which actually participates in the cycle, and this is your active catalyst, which is the 12 electron having the space for coordinating the olefin. So basically, the mechanism starts in this way that we use the active catalyst, and there, when we have a space and it is electron deficient also, olefin come and bind with the rhodium, giving it two electrons. After that, we give hydrogen source to this one, and that hydrogen undergoes oxidative addition, giving two hydrogens split into and coordinating to the rhodium, increasing the electron oxidation state to +2 even more, and electron number 16. After that, when we have an olefin and a hydrogen over there, that undergoes a transfer, and then it would form an alkane here itself. Since both the hydrogen and the alkane part are cis to each other, they will undergo the reductive elimination to give you a final alkane product. Followed by that, since we started with the asymmetric hydrogenation, there we meant to say that how we can involve the asymmetry. You can make your catalyst as asymmetric like chiral. So how can we make it? We can induce the chirality in the phosphine system. So instead of the achiral phosphine ligand, you can use a chiral phosphine ligand. What are the examples of these ones? So the above one is a non-chiral system where the two groups are similar. So there is a plane of symmetry. Whereas if we introduce an AR group, which is any other phenyl group or substituted phenyl group, and the other side is also different, that means it is losing its plane of symmetry, or it is losing its like original character. It is having different groups now. So that would make or ensure the asymmetric hydrogenation to happen, and therefore it would end up giving you two isomers, either R isomer or S isomer, or a combination of both. Based on that, we found out that in asymmetric hydrogenation, we have two isomers, mirror images of both of them. And here we found out like which one is to be measured. The last question that I've given, you have to consider this example and then to find out which one is going to be the major product. So here we found out that S isomer is the major one, even though the mechanism was not telling that S could be formed. But using a Curtin-Hammett principle, this came out to be that S isomer is going to be favorable because the transition state that is involved in getting the S isomer is having lesser energy. So this way we could quantify it. Moving ahead, the next lecture was about the transition metal carbines, and we know that a classification of transition metal carbines into two, Fisher and Straw. What is the basic difference of the Fisher and Straw? Fisher carbene ka example that you can see onto the window, that chromium is there, carbonyl groups are attached with the chromium center, there is a carbon center and attached with OMe and phenyl group. Followed by that, this is the basic difference between the Fisher and the Straw. Fisher carbene, the metal center is actually generally your late transition metals, like after the titanium, you can say, and they tend to form low oxidation complexes. They will be staying in the low oxidation state. Since they are highly electron rich, they will be stabilized by pi acceptors such as carbon monoxide NO group, mostly carbon monoxide carbonyl group. And the carbon center that is there for the carbene, that is electrophilic in nature. And to stabilize it, it actually has the pi donors for in it. Pi donors are OR group, NR2 group, which are having the lone pair. On the contrary, in shock carbene, we have early transition metals, which are having a higher oxidation state. They are electrophilic in nature and they don't have non-pi acceptors. They do have non-pi acceptors because they are already electrophilic. If you're attaching a pi acceptor over there, it will even further destabilize it. And the carbon center is nucleophilic in nature, which is having normal groups like hydrogen, methyl, which is because anyway it is nucleophilic, it does not require any other center to give more electron density to that. Now, taking the Fischer carbene synthesis into picture, Fischer carbene is having, if we talk about the metal carbonyl, we have taken a metal carbonyl complex, and one of the CO groups will be turning into other substrates by treating it with the organolithium compound, which tends to insert the R group into the carbonyl group and forming this particular species. After that, when we treat it with the diazomethane, it would make it to a carbon system, and that is your Fischer carbene. Similarly, straw carbene is a discovery out of the accident because it was intended that after treating this tantalum chloride with the lithium neopentyl, it would give you this particular species, but it ended up giving you a straw carbene, which is, you can say that tantalum is in higher oxidation state, it is a late transition metal center, and carbon over here, it's more nucleophilic compared to that. And these are the other examples with the titanium, where it is also again a plus for oxidation state. This is the Tebbe's reagent. So these are different examples of the shock carbene that we discussed. Moving ahead, we also have a type of catalyst, which is another name, which is called as Dux catalyst. It is having different applications. And where the ruthenium is the center and the carbon here also is nucleophilic in nature. Now, talking about the applications of these catalysts, they are generally being used in olefin metathesis and carbonyl olefination. So we started with the olefin metathesis. The olefin metathesis is basically the CC bond formation between the two olefins. So if you see, this is R and R, this is R dash and R dash. These now R and R dash with the first half. This is going to make a new olefin. So it will release the two molecules of the same olefin, which is a new olefin. Now, carbonyl olefination is something where we have a carbonyl group and we have a catalyst, and it will end up giving you a new olefin and releasing a metal oxide complex over there. Now, olefin metathesis is also having different types: ring closing, ring opening, polymerization of these metathesis reaction. So we are taking a ring closing metathesis where we have an open ring, not a ring open chain system, where this hemicircle is defining that there is a huge number of CH2 groups in between. So if we talk about that, we are treating it with the metal carbene, in presence of metal carbene, this will undergo a metathesis. So these dots will join together, making an alkene. And the other left out groups like CH2, CH2 that would release as an alkene as a byproduct. Similarly, this is the mechanism that we have, that these are the parts, and firstly it will go undergo 2 plus 2 addition, forming a butane type of cyclobutane type of intermediate, and after that retro 2 plus 2 and forming double bond over here. Since we started with this one, we ended up making a new catalyst inside, not a catalyst, but a new intermediate involving the metal center, and that would release your desired product and the olefin. Followed by that, this is an example of the centers, which is an intra-metathesis. Earlier, we were seeing the examples where we are using two different olefins, like inter-metathesis was happening. This is an intra-metathesis where the two olefin bonds are there, and it ends up giving you a new olefin as a product. Now, compared to the Grubbs catalyst, shock catalyst that has been seen for this metathesis reaction, it is having certain limitations, that it is not having much functional group tolerance, meaning that if you are having a ester group, alcohol group, aldehyde group, it is not going to give you much yield, or the reaction might not work. Instead, Grubbs catalyst works very fine. As you can see, the product is on the right hand side. So therefore, it is having wider application in today's time. Now, another point, that ring closing metathesis of diene ions, meaning we have a combination of olefin, alkene, as well as alkyne. If you can see, on our left side, there is an olefin. On the right side, there is an olefin, and in the center, we have an alkyne. It can be just ene and ine also. So firstly, it will undergo, should not be that. Yeah. So firstly, it will undergo the interaction between the alkene and alkyne, and when it will form an alkene, and the other one will go and interact with the second alkene in presence of the Grubbs catalyst, and this is our product that we have formed. Now, to understand the much better alkyne metathesis, we have two alkynes, and if you can see, this is 7 in number. That means there is CH2 CH2 chains over there, and it would end up giving you a new alkyne, making a closed ring, which is a ring closing structure also over here. And if we will see in more details, that we have a tungsten based carbine over here, and we have alkyne. This undergoes 2 plus 2 and forming an alkene. Now, from X-ray analysis, it was found that all the bonds were equal in length. Therefore, they can be rearranged. The bond can be like moved from this side to this one. The resonance they can. So once we get to this one, when they do a retro step, and therefore we end up getting a new metal catalyst and a new olefin that was a product of interest. Now, there is a comparison, like whether we can consider the shock carbene versus Wittig reaction. Wittig reaction is something when we are using a carbonyl group, and it would turn out to be a conversion of olefin carbonyl group to the olefin group. And once we saw that, we found out that Wittig reaction is having certain limitations, that it can't work with the ester, it can't work with the DMF, where the shock carbene can easily work. Why is it so? When it was compared, just a second. Yeah, so it was found that DMF and esters are having less nucleophilic character, and for getting the Wittig reaction, we need more nucleophilic character over there, and that's where shock catalyst beautifully worked in that aspect where the Wittig reaction failed. Now, the last topic that of was interest is the comparison of the Fischer carbene as a carbonyl equivalent. Again, here we found out that Fischer carbene can be considered as a carbonyl equivalent with the more electronegative environment and more double bond character. Why? If you see that this A can be your CrCO5, if it is CrCO5, that becomes a Fischer carbene. If it is oxygen, that becomes your normal carbonyl. So if X is equals to O, which is this group, O or NR, like if you're having an methoxide, butoxide, ethoxide, so this becomes one group. And if you have an amine group, that is another group. So here the rotation barrier of this CX bond is very, very important. If that rotation barrier is very high, that means this electronegative character of this particular group is too high because of the double bond character also. So everything becomes higher, and that ensures that it is having more double bond character, and it can be used for more proper application. So when we were having oxygen over here, the rotation barrier was calculated as 12 in case of OR. In case of NR, it was 18. When we introduced CrCO5, that means in case of Fischer carbene, it turned out to be 14 and greater than 25. So that's where when we compared the Fisher carbene and the carbonyl group, the Fisher carbene was found to have more electronegativity, and based on that, it was having more double bond character. So now in this particular case, because of this property, it can also undergo the interconversion very easily. We have an OMe group over here. If you want to change it to tertiary butoxide, you just treat it in presence of tertiary butanol. It would convert it into OMe to tertiary butanol, and it can go back to methoxide group if you treat it with methanol. Similarly, when we treat this Fischer carbene with HNR2, it gives us NR2NR, and again, the Fischer carbene is having an application in aldol reaction where you can see that we are using a Fischer carbene and a carbonyl group, and it turns out to be a OH group over here, which is a diastereomer. And the last application of these carbene was the cyclopropanation, where the commonly catalyst were palladium plus 2 for diazo methane, rhodium catalyst, and copper iodide for diazo ester systems. So this is what we have done, and certain examples that we problem session that we had is that considering this one, you need to find out which one is going to be the major product, and firstly, what is the product over there. Second, we gave a different type of catalyst and the combination onto the right side, and you need to find out the which one is the right combination. Say, for example, Fischer carbon, the metal has to be in a low oxidation state. Shock, the metal is would be in high oxidation state. Also, it found that metal can be titanium because it comes under early transition system. So on and so forth. The third question was regarding that for X equals to these many different substituents. So which catalyst is going to be the most suitable for canning of this reaction? So in this case, you need to first understand that we have an olefin over here and it is undergoing metathesis. So this is a metathesis reaction which can be done in presence of Grubbs, Stock, Fisher, but not with the Osborne catalyst because that Osborne catalyst is valid only for the hydrogenation of your system. So that D option is anyway not correct. But out of all the three, we have already noticed that Grubbs catalyst is having the functional group tolerance, and they are the one which is giving the more application in this regard, not the short one. So option A is correct. So in this kind of way, in this way, your questions can be framed in the assignments and in the future paper. And this is the fourth question that I've given you for homework. That just find out using the same example. I've just change the bit with the transition states, energies, and all those things to find out which one is going to be the major product and what is the reason for that. So if there is any question, please let me know. Otherwise, we can end the session. So I'll be uploading this material slides onto the link given. So you can access these slides at any point of time, and you can also go back and watch the videos of both professors and this live session as well. So otherwise, we'll meet you in next Saturday from 6 to 8 p.m. Try to come back with your full preparation. Like you should have gone through the lectures, right? So that it is more convenient for me to make you understand the concepts, and then you can come up with your questions also. So with that, I would end up this meeting. Thank you for joining.